Good evening everyone. Thank you for joining me for this video. I am Mr. Ish. We're looking here at this complex binary integral form involving sine and cosine where each has a specific exponent and they're designated as m or n. In this video specifically, the three questions we will look at, one of these exponents must be odd or they can both be odd. In this video, we're not looking at any instance where m and n are both even exponents because that's a subject matter for another video. When they are both even, the m and the n exponents, the question is slightly more complex and more intricate. In this video, we will limit ourselves to this specific instance where at least one of these exponents must be odd. With each question that we look at, the three in total, we will clearly delineate all the procedures that are involved and all the necessary steps you must take to handle this type of an integral. Our first question is the sine square x and then cosine cube x dx. We have to integrate this. And now you're seeing that the cosine is odd. When you see at least one of these are odd, the first thing you're going to do is you're going to push out a single item of that odd one and push it aside into your integrand, but you'll separate it from your main part of that same function. You see here we have a cosine cube x, we'll have a cosine x, and then a cosine square x dx. You see I pushed out a single component and I separate the cube into that. This item which has been pushed outside must cancel somehow later on by the polynomial substitution technique. The remainder of that, which is the cosine square, must get affected by the trigonometric identity sine square x plus cosine square x equals 1, because now that must get converted into a form of a sine function. Anything which is bound to get cancelled out, everything else must convert into the other function. And you'll see what I mean momentarily. Sine square x, here you'll have a 1 minus sine square x. You have a cosine x dx. We have to use polynomial substitution. If u is equal to sine x, how do I know I'm using u equals sine x? Because I must cancel out the cosine x. And only the way I can do that is I can make u into a sine x and then it'll bring in the cosine x in terms of the derivative. Du is equal to cosine x dx and dx is equal to du over cosine x. Now we'll bring in the substitutions. U here becomes a u square. Here we have a 1 minus u square, right? And then here we have a cosine x du over cosine x. You see how this thing is cancelled out by the polynomial substitution. Now everything is a simple polynomial. You have a u square minus u to the 4 du, and you can easily integrate this. N plus 1 divided by n plus 1, you'll have u cube over 3 minus u to the 5 over 5, but we can substitute the sign. You'll have a sine cube x over 3 minus sine to the 5x over 5 plus c. You can do common denominator, isolate a sine cube x and all of that, or you can just keep this as your answer and it should be right. Now remember, in this type of a complex binary integral, you're looking for the component which is odd. You push out a single component which will later on cancel through the polynomial substitution technique. The remainder of that same function will get substituted for the other function by means of this, and everything will eventually become a polynomial integral style of question. Question number 2, the sine is odd. So we'll bring out a single sine component and we'll rewrite this. Now sine has become even and we have a cosine 4x and then we have a sine x. Now our question here was sine to the 5x, cosine to the 4x dx. I pushed out a single sine component and I've brought it right over here. This sine must cancel somehow by polynomial substitution technique, and the remaining of that must get converted into a cosine utilizing that identity. This sine to the 4x must get converted into a cosine, and you can use it using that identity cosine square x, and then you square it. It's very well equal to sine to the 4x. You have cosine to the 4x, you have sine x dx. You got to cancel sine x, and the only way you can do that if u is equal to cosine x, because then that derivative will bring the sine and that will easily cancel it out, and dx is equal to minus du over sine x. The minus will come right here outside. We'll have now 1 minus u square. I'm doing all the substitutions here, and u to the 4. We'll have a sine x du over sine x. These sine x cancel out. You have to open up all of this. You'll have a 1 minus 2u square plus u to the 4, all multiplying with u to the 4 du. When you open that up, this part right here, you'll have u to the 4 minus 2u to the 6 plus u to the 8 du. Now this part is easy. We can integrate it and substitute it and open it up with a negative all in one step. Our final answer will be this, minus cosine to the 5x over 5, because this will become n plus 1 divided by n plus 1. Here we'll have a plus 2 cosine 7x over 7. Here we'll have a minus cosine 9x over 9 plus c, and this can serve as a good final answer. Again, minus cosine to the 5x divided by 5 plus 2 over 7 cosine 7x minus cosine 9x over 9 plus c. We isolated in sine x because the sign was odd, which later on cancelled by the polynomial substitution technique. The original portion of the sine, the remainder part, got converted into cosine by means of the identity, and everything became a polynomial. Not too hard. Our last question is this. We have both items which are odd, sine cube x and cosine cube x. When you have the situation, you only pick one and you work with one. You don't convert them both into even by separating a sine and a cosine x. That'll complicate everything. Here you only pick one specific function and you work with that. I want to pick cosine x and move that out. And then you'll have a sine cube x over here, which can stay as that, nothing wrong with that. You'll have a cosine square x, cosine x dx. This cosine x must get cancelled by a substitution, and the remainder of that must get converted into sine x by the identity. We have a sine cube x. Here we have a 1 minus sine square x. We have a cosine x dx. So you can see the procedure is not hard. Cosine x must get cancelled out, so you know u is equal to sine x because only its derivative will cancel it out. And dx here is equal to du over cosine x. Bring in the u into everything. You'll have a u cube 1 minus u square and then cosine x du over cosine x. These will cancel out. You can open this up. You'll have a u cube minus u to the 5 du. Easy from here. Bring in the antiderivative easily and do the substitution, the u substitution, and we will have u to the 4 over 4 minus u to the 6 over 6 plus c, and u here all along with sine. We'll have sine to the 4x over 4 minus sine to the 6x over 6 plus c. If you want to take the extra effort, you can do a common denominator, adjust everything, and isolate a sine to the 4x, and then rewrite everything in a more simplified answer, or you can leave this as is. Again, this procedure here is not difficult. We looked at everything here in terms of either an odd, one of them being odd or both being odd, but nothing here was in terms of both of them being even. That's a material for another video because that's slightly more complex. But lastly, I want to reiterate the procedure. Always look for the component that's odd. Push a single item out from your integrand aside, and then the remainder of that will get converted into the other function by means of that identity. The item that's pushed aside will get cancelled by the polynomial substitution technique, and everything in the end becomes a polynomial integral, and you carry it through with the resubstitution at the end. Not a difficult procedure. Thank you for watching. Have a nice day.